Design criteria are restrictions on how one designs. They can be thought as of the givens for a roadway design project. They're scattered throughout the Green Book, mostly in chapters 1 and 2, but throughout other portions as well. And it's a collection of design dimensional values, typically based on knowledge from operations and research. So most of these are empirically derived values. And they're important for providing consistency, quality, appearance, and performance of a highway system. And these are usually made at the policy level. The engineer, though, does have some flexibility. Most design controls are achievable, but some may not be achievable. And if that's the case for a certain set of design controls, you must get clearance to change or approval if you deviate from those values. This is guidance from the North Carolina Department of Transportation, and I think this is an excellent overview of the selection of design controls. Their documentation states that the selection of the correct design criteria for a project is one of the most important tasks that confront the highway designer. There are unlimited factors that can affect the design of a particular project, making it impossible to provide explanations for them. However, design criteria is more strongly affected by the functional classification, design speed, traffic volumes, character and composition of traffic, and type of right-of-way. Usually when full control of access is purchased, the design standards are much higher than on a project with partial or no control. Other control factors, such as unusual land features, safety, and economics, are always highly reflected in the design criteria. Typical sections show the planned cross-section of a roadway from a general perspective. They show details such as widths for lanes and shoulders, slopes of pavement and ditches, and how the road will tie into the existing terrain. Typical sections give the general design of the roadway cross-section and are customized based on the needs at a particular location. One list of design controls comes from the Federal Highway Administration in the form of design exceptions. These are design criteria denoted for having substantial importance on safety and operational efficiency. Formal exception is required if the controlling criteria are not met on the national highway system. These include the design speed, lane width, shoulder width, horizontal curve radius, superelevation rate, stopping sight distance, maximum grade, cross slope, vertical clearance, and design loading or structural capacity. Agencies have plans and policies in place when design exceptions are needed for one of these 10 criteria. All 10 controlling criteria apply to high speed, such as interstate highways, other freeways, and roadways with design speeds greater than or equal to 50 mile per hour roadways on the national highway system. The stopping sight distance applies to horizontal alignments and vertical alignments, except for sag vertical curves. On low-speed roadways on the national highway system, only the following 2 criteria apply: the design speed and the design loading structural capacity, which are fundamental criteria in the design of a project. Exceptions to these criteria should be extremely rare. The Federal Highway Administration expects documentation of design exceptions to describe all of the following: specific design criteria that will not be met, the existing roadway characteristics, the alternatives considered, comparison of the safety and operational performance of the roadway and other impacts such as right-of-way, community, environment, cost, and usability by all modes of transportation, the proposed mitigation measures, and compatibility with adjacent sections of roadway. There are numerous reasons for needing a design exception, and these can include impacts to the natural environment, social or right-of-way impacts, preservation of historic or cultural resources, sensitivity to context, sensitivity to community values, and construction or right-of-way costs. The overall design exception process begins with determining the costs and impacts for meeting the design criteria, developing and evaluating multiple alternatives, evaluating the risk and mitigation measures, documenting, reviewing, and approving the design exceptions, and finally, after it's constructed, monitoring and evaluating its in-service performance. Functional class is important, showing us the relationship between mobility and access. Freeway is the highest type of arterial and the highest functional class in terms of mobility. On the other end of the spectrum, we have local streets and cul-de-sacs providing the highest levels of access but low levels of mobility. So this is the spectrum that we see in terms of functional classification. And typically, collector streets will carry somewhere on the order of 1,000 to 15,000 vehicles per day. Minor arterials will carry between 15,000 and 35,000 vehicles per day. Arterials will carry 35,000 or more vehicles per day. And often on urban freeways, we'll see 100,000 vehicles per day or more. On local streets, typically will be under 1,000 vehicles per day. The width of your roadway is an important design feature, and it varies by functional class. For interstates and freeways, you will probably have a typical right-of-way for a 4-lane section from 250 to 300 feet for rural projects, and for urban projects between 150 and 200 feet. For rural arterials and collector projects, you may have right-of-ways that are between 100 and 150 feet, or for a 4-lane between 150 and 250 feet. Urban arterial projects will have a minimum right-of-way to account for the built-up area that it's in. So the right-of-way will typically be a minimum distance of 5 to 15 feet beyond the construction limit. So trying to minimize that right-of-way to the amount possible. Shoulders are another important characteristics of our roadway. We can see in an urban area, and particularly in a freeway scenario, shoulders provide room for crash avoidance, where disabled vehicles can be stored. Maintenance activities, law enforcement, emergency response can all utilize that shoulder for their activities. Also, shoulders typically improve drainage and provide some structural support for the pavement itself. Shoulders also can help with other criteria. So the presence of a wide outside shoulder on this roadway moves that barrier further away, providing additional stopping sight distance on this bridge rail along this horizontal curve. This is some design criteria from NCDOT, suggestions on the width of the shoulders for the design year traffic volumes and whether or not guardrail is present. So the amount of usable shoulder that is recommended varies from 4 feet up to 10 feet on freeways and expressways with higher truck volumes, and even up to 12 feet when the truck volume exceeds 500. The clear zone defines the forgiving roadside concept. So it's the lateral space adjacent to our travel lanes that allow a vehicle, an errant vehicle, a vehicle who leaves the travel lane, to hopefully safely recover or stop their vehicle. And this is the traversable and unobstructed area extending from the edge of the travel way. The width will vary based on the crash risk, the design speed, the slope, and the cost of treatment. This information is provided from the Roadside Design Guide. Table 3.1 provides general guidance, and Table 3.2 provides us with adjustments for horizontal curves. And this illustration defines the 3 key types of slopes we have. Although it's not shown, critical slope is a 1 to 3 slope or steeper, and we want to try to avoid those slopes if possible. We typically will have to have some type of treatment if we have a critical slope in our roadside environment that penetrates the clear zone distance from the table we saw previously. The most desirable type of slope in our clear zone is a recoverable slope, and this is a slope that's 1 to 4 and flatter. Typically the flatter the better. The flatter it is, the more easily a vehicle who leaves the roadway can recover or slow down their vehicle. And then in between those slopes is a non-recoverable slope, and that really just basically interrupts or kind of pauses the clear zone. So we see in this image, we have a clear zone distance, and we have our shoulder that's part of our clear zone. We have a recoverable slope that's 1 to 4 or flatter, but then we encounter a non-recoverable slope, and that's a slope again between 1 to 3 and 1 to 4. And because we have this non-recoverable slope within our clear zone, we need to provide an additional clear runout area that is at least 10 feet, but needs to cover the amount of that clear zone distance that is interrupted by our non-recoverable slope. Pavement cross slope is an important cross-section design element. The cross slope drains water from the roadway laterally and helps minimize ponding of water on the pavement. This prevents maintenance issues and also minimizes icing from occurring on poorly drained pavement. On roadways with curved cross sections, the cross slope moves the water to a narrower channel adjacent to the curb, away from the travel lanes where it can be removed. Cross slopes that are too steep can cause vehicles to drift, skid laterally when braking, and become unstable when crossing over the crown to change lanes. These conditions are exacerbated by icy, snowy, or windy conditions, and both maximum and minimum criteria exist for cross slope. A formal design exception is required wherever either cannot be met. The cross slope criteria apply to typical tangent alignments also. On high-speed roadways, the normal cross slope is between 1.5 and 2%, with a cross slope break, which is the algebraic difference in the slopes between the lanes, at the center line not exceeding 4% in areas of intense rainfall and where there are 3 or more lanes in each direction. Additional cross slope may be necessary for adequate drainage. Accomplishing other design features like superelevation transitions, pavement warping at intersections will inevitably require removal of cross slope in spot locations. These cases are routine and necessary in design, and a design exception is not required in those cases. In addition to the cross slope of the lanes, the cross slope break on the high side of the superelevated curves should not exceed 8%, and between the edge of the lane and the shoulder should not exceed 6%. Typically, most slopes over 7 feet will require guardrail, and we can see that on this graph here, looking at the fill section height and the slope, in particular when the slopes are steeper than 4-to-1, and then certainly at a 3-to-1 slope, barriers are typically going to be warranted. So we talked about normal crown being between 1.5 and 2%. Emax, or the maximum superelevation, or the amount of banking in the curve, lessens the radius needed. And so superelevation is not always needed if you have gentle curves, but if you have sharp curves, you'll need larger superelevation rates. And this also depends on the weather and urbanization in an area. And values of the maximum superelevation rate range from 4% to 12%. And typically, if you're in an area that has snow and ice as a common feature on the roadways, 8% will typically be a maximum superelevation rate. And driveways and intersections require a low superelevation, typically 4% or 6%, depending on the location. Horizontal curves are important to design for, and some of the important characteristics are the design speed, the maximum superelevation rate that we just talked about, and the side friction factor that's a component in there as well, which relates to a minimum radius. So we typically want to have design with a radius larger than that minimum radius, and that also allows us to adjust that superelevation rate downward. So these are for maximum superelevation rates between 4 and 8%. We also have values between 10 and 12%, and there are additional tables in the Green Book providing more details as you adjust down from that maximum superelevation rate. For vertical alignment and vertical curves, we have maximum grades that are recommended. We also have design values from the rate of vertical curvature for various vertical curve types and sight distance criteria. In terms of the grade, here's an example of a steep downgrade with a horizontal curve at the base of that grade, and this is going to be a place of potential issues from a crash perspective. We're going to see vehicles exceeding the operating speeds, the safe operating speeds, and then leave the roadway as they transition from this tangent to the curve at the bottom of this grade. So a little more detail here on the vertical curves. This table shows us the design controls for sag vertical curves and our K value, or the rate of vertical curvature that I mentioned previously. when looking at maximum grades. So this rate of vertical curvature tells us the length of curve per percent in algebraic difference in the intersecting grade. So it tells us how quickly we can transition from one grade to the second grade. So transitioning from the entering grade of the vertical curve to the exiting grade is defined by the rate of vertical curvature. When we're looking at stopping sight distance for a sag vertical curve, what we're really interested in is nighttime conditions and how far the headlights are able to illuminate the upgrade that's coming out of the curve. And so this is an example. Our headlights can only see so far along. We can't see what's no longer illuminated by our headlights. And the typical assumption is that we have a 1 degree of deflection as our vehicle transitions down the entering grade and starts to go up the upgrade. So this is really the typical condition we're looking for a sag vertical curve, nighttime conditions. For a crest vertical curve, really looking at daytime conditions, and we can see this vehicle as it transitions over this crest vertical curve that it starts to disappear. And so what we're worried about from a stopping sight distance perspective is if that vehicle is stopped just barely over that crest curve, as the next vehicle comes, can it see that vehicle, and can the driver decide that there's a hazard and react in a safe and predictable manner in which they don't lose control? So that's what we're worried about with stopping sight distance at a crest vertical curve. We can have other sight distance issues. Here's an example of a railroad crossing over a highway, and the railroad bridge itself, as well as the cars on the railroad tracks, can block or obstruct the view from drivers. So making sure that there isn't some kind of sight distance issue for these particular locations is very important. Design speed, this is really not a specific design element. There's really not something you can go out to a roadway and necessarily understand the design speed. It really, though, impacts a lot of the other criteria. As we saw talking about these other elements, design speed plays an important and consistent role in a lot of those criteria, and it establishes a range of design values for many of those other elements. The Green Book has design speed recommendations from 15 to 80 miles per hour in 5 mile per hour increments, so a lot of information that's provided in the Green Book. And these are the maximum safe speeds under favorable conditions. In most locations, the design speed is about 5 or 10 miles per hour greater than the speed limit. And the design speed's particularly important for horizontal and vertical curvature. And the design speed can differ on different segments of a project, although consistency is very important, and there's lots of new tools to help us establish and identify where we're going to have disruptions in consistency. And drivers, particularly local drivers, will begin to learn and know the design speed of a road. If you think about a road you're familiar with, you will tend to know, what curves are able to be traversed close to the speed limit or much under the speed limit, and gain that real sense of what the design speed of the roadway is. So roads that you're familiar with, you're going to develop some intuitive perspective of that actual design speed. This image shows a curve that likely is having some difficulties with drivers understanding the design speed. We can see chevrons in this curve. We can see tape along the barrier here to help alert drivers of the curve. The barrels may or may not be a permanent fixture here to help alert drivers of the curvature. And there's a difference between the designated design speed, and that's what we've been talking about, where we have a selected speed that's used to determine various geometric features of the roadway, and then the actual inferred design speed and the operating speeds of drivers. So as a driver drives along a roadway, they're going to infer a design speed and start to understand the characteristics of the road and what speed is a safe speed for them to travel and what speed is a safe speed for them to operate at. And when we disrupt those expectations, when we violate those expectations of those drivers, we're typically going to see crashes and collisions as a result of that mismatch of our design speed, and then the inferred design speed and operating speeds that result from that. So that's something we've got to be very careful for on what we communicate to the driver and how they're going to interpret the actual design. Speed is an very important component. This is a summary of various studies that have looked at the relationship between changes in travel speed and the crash rate. And what this graph essentially shows us is that a speed reduction of 1 mile per hour corresponds to a 5% decrease in the crash rate. And we can also see that in reverse, that a 1 mile per hour increase in the speeds, the average speeds of all the vehicles, corresponds to a 5% increase in crash rate. So the speeds are very important. So if we can take an existing road, and if we can change that speed, if we can adjust that speed, particularly downward, if we can decrease the average speed of the vehicles on that roadway, we typically will see a decrease in the crash rate, as long as there's consistency among all drivers and we don't create an issue where some drivers are now driving faster and some are driving slower. Sometimes we'll have issues in those cases. But again, speeds are very important in the relationship with the crash rate. Lane width is another very important component that affects the safety and operations of a roadway. And it's important to think about how lane widths are going to be interpreted, how they will affect drivers. And there is a kind of happy medium. There's no overall conclusive studies that show the direct relationship between lane width and crash risk or crash rates. But certainly, if lanes get too wide, you're going to induce higher speeds. If lanes are much too narrow, you're going to have vehicles that are too close together, particularly with heavier and larger vehicles. They're going to create too much friction there. So there is this kind of happy medium of lane widths that we should consider and think about when we're designing a roadway and choosing an appropriate lane width for that roadway. Vertical clearance is a very important component, particularly of our national highway system. These are the adopted criteria for various highway functional classification, and these are used to provide at least a 1 foot differential between the maximum legal vehicle height and the roadway itself. We've got to think about additional allowances for resurfacing. So when we come back in and we put down 1 inch or 2 inches of asphalt, how does that change that clearance that's provided between the roadway and the structure that's above it? Making sure that we apply this to the entire roadway width, both the travel way and the shoulders. And if this is violated, a design exception is needed from the Federal Highway Administration. Here's an example when vertical clearance became an issue. So the vehicle was possibly too high or the bridge was too low, depending on what perspective you're looking at. And obviously this creates a substantial amount of damage to the bridge structure itself. And then it obviously closes down the roadway, causes debris on the roadway, stops the traffic behind it, and it's going to create a long detour route to possibly as they try to fix this bridge. Design vehicles are also very important to consider. The typical default design vehicle is a WB67 truck. This is an example of a greenway, and for some reason a garbage truck was trying to navigate this greenway that was designed for pedestrians and bicyclists. And as you can see in this curve, it was pretty much stuck, wasn't able to navigate any further past this point. And just to me brought up a good point about, what is the largest common vehicle we expect on the highway you're designing in the design year. So it isn't a once in a lifetime type of event, but what is that largest common vehicle that you're designing for? A lot of the highway dimensions are going to be based on that design vehicle, particularly at intersections. And some of the characteristics that impact that design are just the overall size. So looking at the lanes and shoulder widths, vertical clearances. Off-tracking is also important, so looking at intersections and the turning radii, the traveled way widening for curves, pavement widths. All those are going to be controlled by the off-tracking of the design vehicle. Storage requirements as well, turn bay storage lengths, bus turnouts, parking lot layouts. Sight distance, so thinking about the eye height and braking distance, which vary between passenger cars and trucks. Acceleration and deceleration are going to have an impact, particularly your traffic signals, intersections, the vehicle stability. So certain vehicles with higher centers of gravity may be more prone to skidding or overturning, which can affect the design speed and superelevation design components. Another thing to think about, we talk about design vehicle a lot, but you may also think about what's known as a control vehicle. And a control vehicle is a vehicle that will infrequently use a facility, but must be accommodated on those occasional incidents. And so with a control vehicle, you may allow encroachments into the opposing traffic lanes. You may assume that they'll need to take multiple point turns, as this garbage truck was doing on this greenway. They had to reposition themselves several times to try to make it down this greenway path, or maybe even minor encroachment into side streets. And a condition that uses the control vehicle concept arises when you have these large vehicles turning at intersections with low opposing traffic volumes. So a moving van in a residential neighborhood or a once per week delivery at a business, those are conditions that you may say, okay, we're not going to fully design our roadway to handle this on a normal basis, but we're going to want to consider it for infrequent uses. And when you have these large vehicles that rarely turn at an intersection with moderate to high opposing traffic volumes, such as emergency vehicles, could be another case where you consider those being thought of as a control vehicle instead of a design vehicle. Again, the design vehicle is a vehicle that must regularly be accommodated without encroachment into the opposing traffic lanes. And this is when you have large vehicles that are going to regularly turn in an intersection with high volumes of opposing traffic. And that may be a bus route. So if you're on a roadway considering bus routes, you're probably going to need to have those buses incorporated as a design vehicle and not a control vehicle. So this is a summary of some of the common design criteria and design controls that go into a highway design. And each of these need to be considered, and each of these have effects on the other ones, and sometimes they are even conflicting with each other. So it's a very iterative process to consider these various criteria.